Enter value iteration. Richard Bellman started his career studying mathematics, but due to World War II, he took up teaching electrical engineering as part of the war effort. He made numerous contributions to mathematics and computer science, but we're going to focus our attention towards his work on markup decision processes, or MDPs. Bellman's strategy was to reduce the problem down to their simplest possible state, and then figure out how to use recursion to solve larger, more complicated problems. So here's the simplest possible lake we can make. We only have two positions, our states, that we can be in. One is the starting state with the gumdrop emoji, and one is the ending state with the exit ramp. Also keeping things simple, there's only one action we can take, which is to move right. Here's what the MDP would look like for our tiny lake. State 0 would be our starting state. Action 2 is moving right, which would take us to state 1, which is our ending state. Why action 2 and not 0? That's the value AI Gym assigns for moving right. 0 is left, 1 is down, 2 is right, and 3 is up. When we move from the starting state to the ending state, we pick up a reward of 1. How did I come up with this number? Let's look at a more complicated case. I've added another row here. This time we have a whole death. As the engineer setting up this environment, I'm going to make the argument that dying is the opposite of living. So after normalization, we get a +1 if we leave the lake, and a -1 if we die. Playing around with the rewards and seeing how it improves the performance of the learning of our AI is called reward shaping. For video games, using the change in score points, or for finance, using the profit and loss explained, are already powerful reward functions. Another note about this more complicated situation is we now have a loop between the two top states. Why not use a depth-first search to get to the exit? Well, there might actually be some types of games where the best strategy is to move back and forth between two states. There's a trick in the original Mario where you can keep tripping on a turtle shell for infinite lives. I've included a YouTube link for important research purposes. A real-life example is koalas. Their best strategy is to alternate between eating and sleeping. In order to solve for these types of situations, Bellman was inspired by delayed gratification from psychology. His goal was to mathematically capture the value of a current state based on the future states it could lead to. Here's the equation Bellman came up with to solve this type of problem. We're going to find a numeric value, or V, for each state, or S. We'll define that as any reward we receive given the action, or A, that we take in our current state. Then, we'll add that to the discounted value, or gamma, of the new state that we end up in, or S prime. That's what the apostrophe by the S on the right means. The discount factor is usually between 0 and 1. Let's start simple and set the discount to 1. If I do that, I value tomorrow as if it were today. For example, let's say I win the lottery and get $100. Woohoo, that's great. I see that as $100. Now let's say I win the lottery for $100, but I can't collect until tomorrow. If my discount is 1, that's just as awesome as if I could collect today. But let's say my discount is 0.5. The $100 tomorrow is worth $50 to me today. The effect of this gets multiplied with each time step. For instance, $100 2 days from now is $50 to me tomorrow, and $25 to me today. So what about the opposite extreme? What if my discount is 0? If you practice yoga or meditation, you might have heard about living in the moment. A discount of 0 is the ultimate zen. $100 today is great, but if I was told I would get it tomorrow, it wouldn't affect me. All my decisions would be based on the now. So what discount should we give our gumdrop? It depends on what our goals are. Do we want to prioritize short-term gains over long-term successes? In practice, many people choose a discount of 0.9 to start, and then will adjust depending on their goals. Okay, so back to the Bellman equation. Even though this equation is simple, it's extremely powerful, and is still the basis for popular reinforcement learning algorithms today. We now know how to assign a numeric value to a state, but what if we have multiple possible actions? Which one should we choose to update this equation? For that, we'll introduce something called the policy function. This is where the learning of our agent starts coming into play. Our goal is to find a function that takes state information and recommends an action for the agent to take. For now, we're going to be greedy. Our gumdrop will look at each action it can take and will choose the one that leads to the highest value state. There are other strategies for coming up with the policy, but they'll have to do with assigning each action of a value. If we follow the best valued action, then we're following what's called a locally optimal policy, and we get pi, a fancy star. So we're going to modify our Bellman equation to look like this. This is mathematically expressing our greedy algorithm. We'll update the value of our current state to be the reward plus the value of the highest valued state we can reach within our current state. Nice. We have a way to find the value of a state. This was Bellman's original strategy for how to use it. We'll have two arrays, one to represent the current value of each state, and one to represent the value of state prime. I've laid out these arrays to be the same shape as the lake, but the structure of this array is up to you, and different strategies may be optimal depending on the type of problem. For reference, I have the location of each state in the green box called state map. Our ultimate goal is to find a policy, or what our gumdrop should do in each state. For that, I've created a policy map on the bottom left in yellow. We're just getting started, so everything there is none for now. I'm going to loop through each state and calculate its corresponding S prime value. For state 0, I can reach state 1 and state 2 by going down and right respectively. So I would look at the current values for each of these. Since we're just starting this process, both of them are 0. However, the value of the states do not capture the impact of rewards between transitions. If we choose state 2, that's a reward of -1. So we'll use state 1 to calculate the value of state 0. With the Bellman equation, we get 0 plus 0, so the resulting value for state prime of 0 is 0. We'll keep track of what action we used to perform the calculation in our policy map, which was A2 in this case. Now, we do the same thing for the next state, which is state 1. Unlike state 0, we can pick up a reward of 1 by moving down. That's greater than 0 by moving left, so we'll use A1 as our action. Since state 2 and 3 are terminal states, they have no actions associated with them, so their value remains unchanged. There is one handy trick to note here. Because they are terminal states, and there's only one way to get to them, we could get the same result if we set the value of state 2 to -1 and the value of state 3 to 1 and drop the rewards from our MDP. When we get to doing this in practice, taking advantage of this mathematical trick can help save us a lot of engineering effort. We're almost done with one step of value iteration. To finish it off, we'll take our prime values, multiply them by gamma, and set them to our current values. Finally, we can reset the prime values. If I want it to be absolutely mathematically accurate, I should have a separate rewards array because the gamma does not apply to the rewards that are picked up. But for this simple problem, it's okay if we combine them, so it's rewards only tied to terminal states. Bam! One step down. We'll keep doing the same thing until the changes in the current value are sufficiently small. We get to choose what sufficiently small means as the engineers. For this lake problem, there will be 0 change in 2 more steps of value iteration. Here's the results after 2 iterations, and we would get the same thing if we were to iterate again, so we're done. If we look at the policy map, we can see the optimal strategy, no matter what state we are in. Starting from state 0, the strategy would be to go right and down. This is what the process would look like in code. The labs are going to do a better job of breaking it down and visually showing what is going on than I can just verbally describe. So here, I'm going to describe it at a high level. I've set up a lake here having -1 being the location of a death hole, and 1 being the exit ramp. Next, I set my discount in delta, or how little change needs to happen to be considered done. In the while loop, the code will keep running value iteration until the values returned from iterate value are less than our defined delta. In the iterate value function, the prime value and policy arrays are initialized. Then each state is looped through using the current value of each state. I am cheating a little bit here. A good chunk of the engineering work is in the get max neighbor function. Conceptually and mathematically, it's not so tough, but for each environment that I deal with, I would need to engineer a function that identifies what the neighboring states are. For Frozen Lake, I needed to craft a function that checks if I was up against a boulder, or if the neighboring state is a hole of death or an exit ramp. In practice, reinforcement learning specialists are both machine learning engineers and game developers. Here's the results after we run the code. It takes 6 iterations for the value to finish updating in our value mapping array. At the same time, we'll get the optimal policy mapping in yellow on the right. Pretty cool, huh?